Hi, welcome to functions, first derivatives, and second derivatives. This is our last lesson for this year for NTI and Honors Calc. The beginning of this unit was a little bit difficult to introduce because you hadn't heard of derivatives before, but now that we're here, we have at least worked with them. We know how they function as equations, but what do they look like as graphs, and how do those derivatives and other derivatives, so like second derivatives, function in comparison to the original function? That's the question we're exploring right now. So we have this idea of taking multiple derivatives, and practically if I'm just taking motion as the token example of taking a derivative and being able to understand something practical from it, we can take a position function. Let's say that position is s of x. Then the first derivative of position is going to be velocity, if x is that time variable. Then the second derivative of position, that's going to be acceleration. So it's practically good for us to look at that from maybe a physics or engineering perspective, for example. So this is some notation here for you on the original function, of course, first derivative, second derivative, and then the nth derivative. We can denote these things just with that superscript next to the f. And I wanted to look back at the functions from our first lesson to kind of use them as the to show off the characteristics that every original function and then the first derivative as it applies to that original function and the second derivative as it applies to the original function, how those all work together. So if we look at the original function, this 1/3 x cubed, we can use this function's to plot the y values of f prime of x. We know that's the derivative, so this is slope. We can use that function's slope to plot the y values of f prime of x. So if we were to draw tangent lines, we can take those as spots where we can take a y value from those slopes, and we can plot those on this blue graph. So if this function, the original function, is increasing, then f prime will be positive. So the slope will be positive. If the function is decreasing, then f prime will be negative. Makes sense? We see the function increasing all the time. So, I take that back, except for this spot in the middle there at 0. So this function is always going to be positive. The y values are always positive, except for the x value or the y value at x equals 0, which is also 0. So this graph is never negative. It's never decreasing. The original function is never decreasing. So the slope, that first derivative, is not going to be negative. Now, let's just say, for example, we don't look at, we ignore that this is the first derivative. Let's just call this the original function. And we take that same example, and you don't have to write any of this down, don't change anything. Let's say this is the first derivative from that original x squared. Now, this clearly shows that the function is decreasing because the first derivative is negative. then it's increasing because the first derivative is positive. Okay, so there we have that. And moving on to this first derivative, we can use this function's y values. Oops, that should be blue. Y values to represent or to recognize the slope of f of x. So just driving home that point that you are looking at a bunch of slopes when you look at this quadratic, if it is labeled f prime of x, which it is. If this function is positive, this is sort of reiterating the same point from before, if this function is positive, f of x will be increasing. If the function is negative, f of x will be decreasing. So now that we have all these relationships, there you can see the can of worms opening up. So if this function is 0, which it is right here, if it's 0, so the y value is 0, that's what these are referring to. If these y values are positive, negative, or 0, then this happens. F of x has a what? So what is happening right here? So it has a horizontal tangent line. It doesn't really fit. Or extrema. And we know extrema is a max or min. So this cubic function has just a horizontal tangent line. That is not a max or min on this function. However, again, if we were going to compare these two functions and say, well, this is the original function, this blue one, and this purple one was f prime of x, then we can see the purple function is 0 when there's a minimum, because now we're taking, now it's like we're comparing the slope of the blue one and representing that as y values in the purple one. But anyway, we'll practice this. Now, the second derivative, as it pertains to the second derivative of this green graph, and I just repeated the same graph just so I didn't have to scroll so much. It's the same one that's up here. My page loads a little slow. Yep, so it's the same one, the 1/3 x cubed. But the purple graph is the second derivative of 1/3 x cubed, and so it's 2x. So I've just taken 1/3 x cubed, taken that derivative to find x squared, and then taken x squared's derivative to get all the way to here. But the second derivative is going to be talking about this. So we can use this function's y values to know the concavity of f of x. Now, concavity is the shape a graph curves to be as it increases or decreases. So concave up, which I'm going to abbreviate like this, CC with an up arrow, and concave down, so CC down, these are the shapes which you can see. So I'm going to do this in halves. So we've got this half, which is increasing, then we've got this half, which is decreasing. Clearly, if we put them together, it would make a U shape. And similarly, with concave down, I'll just put it over here to the side. With concave down, we've got a decreasing concave down and an increasing concave down. So if we put those together, it'd be like this. So a fully concave down piece that increases and decreases. So these second derivatives speak directly to the original function's concavity. So if this purple function 2x is positive, which it is right here, then the original function is going to be concave up, like a cup. So pretty nifty rhyme there. If the function is negative, then it's going to be concave down. You can probably think about what rhymes with down. Like a frown. Yeah, like a frown. There we go. So clearly the concavity between the original function, which is right here, that's f of x. If you need to label this as f double prime of x, second derivative, then you can see the concavity. If the function is 0, then f of x has an inflection point. So if f double prime of x, if the second derivative is 0, then there is an inflection point. So what we're looking at on the original function is an inflection point, which is a point where the graph changes concavity. Right, so this is going to be the first video I want to put out about these interpretations of the first and second derivative as they pertain to the original function. So here's a good point to pause, and then we'll get back together and do some examples. Alright, we're back. These are the example questions that go with the first and second derivatives and the multiple derivatives lesson. The first one we're looking at is giving you two graphs, f and f prime of x, and I want you to think, before we start going, which one is f and which one is f prime of x. So we've got a cubic and a quadratic. Hopefully you're recognizing this green function as f of x and the purple function as f prime of x, because we know we reduce the power from the original function when we take a derivative. So we don't have the equation, we're just working with the graph itself. So the first question is, what is f prime of 3? So you can look directly at f prime of x, and you would look at 3 and notice that the y value is 0. Or you could go to the original function, look at 3, so right here, and then look at the slope of the tangent line, and that slope is 0. On what intervals is the graph of f of x increasing? So again, it'd be pretty easy to look at f of x and say, well, we're increasing from negative infinity to -1, and then 3 to infinity, not included. But it's just as easy to say, well, this graph, this f prime of x is positive when it's above the x-axis, so it's just going to be those x intervals that include those two ends of the quadratic. So it doesn't really matter where you look. It might be a little bit faster to look at the f prime of x just to notice what's going on there. So we're going to increase from negative infinity to -1, and then 3 to infinity, not included. What x values on the graph of f prime of x tell you f of x is not increasing or decreasing at that point? So if we don't have a change in our slope, so In other words, f prime of x is equal to 0 is what we're looking for, then we need to find the x values where f prime of x is equal to 0. So we already have that answer, really. That's x equals 3, but also x is equal to -1. And we can see that the slope of the tangent line is that way on the original function. What's the slope of the tangent line to f of x when x equals -2? Alright, so -2 looks a little strange. It's kind of hard to tell. It's that tangent line I just drew, the pink one. It's kind of hard to tell what that is when x equals -2. So we're going to look directly at f prime. So another way to phrase this question is, what's f prime of -2? And f prime of -2, there's -2, this is definitely going to -2, 5, just because I'm noticing these points that I've drawn, and they're all happening at the parent points of a quadratic. It's just a quadratic that's been shifted right and down. So that parent point at -2, 5 is going to be part of our answer. So the slope of the tangent line to f of x is 5, and it doesn't really look like that if we go back to the pink drawing, the pink line I've drawn on f of x, but it is that way, just because we can see that on f prime of x in that graph. Okay, very cool. Number 2, so the given graph of f prime of x, or given that graph, we are looking at the intervals that the graph is decreasing. So this is f prime of x, and I know you might have to pause to draw, so do take the time to do that, because these graphs aren't there. But on what intervals is this graph decreasing? Now, at first glance, we want to say that it's decreasing here and there on those x values. We know that's not true because that's not f of x. This is f prime of x. So f prime of x is negative where the original graph f of x is decreasing, because that's what we're being asked about. We're not being asked about where's f prime of x decreasing, we're asked about where's f of x decreasing. So it's decreasing, and we're leaving a space there with an open circle. It's decreasing when this graph is negative. So it's decreasing from -3 to 4, union 4 to infinity. Now we're saying the x value of any maxima of f of x. So if we want a maxima, that means our graph, if we can just think about this for a second, that means the original function has to be increasing and then has to go to decreasing, right? Has to increase and then decrease. So our original, or our derivative, ought to be positive, has to go from positive to negative. So is there a piece on f prime of x, that graph, that goes from positive y values to negative y values? And there is, because we have this piece right here that goes from positive to negative. So one of our maxima, if we have just one, is at x equals -3. And we don't have any others for a maxima, that is, because we don't ever go positive again. So we can't go back to negative. Now, if we're finding a minima, that means we're going from decreasing to increasing, right? And we can see the concavity in it as well. It would be a concave up piece, but that's not all too relevant. And that would mean that f prime of x goes from negative to positive. So we actually don't have any spot because we never go from blue, which is negative, to that yellow. So none. We don't have an x value like that. Lastly, well, 3 and 4 are tied together. We're sketching this graph, and we're going to use it to we're going to use the items we're given based on what the previous notes were about to find f of x. So we have -4, 0, 1, and 3, 0. We know that those points are on the graph, and then we know that -4, -4, and 0, 1 are points of inflection. So these guys. Okay, cool. I'm not quite sure what that's going to look like exactly, except that a point of inflection could look like, you know, it could change from concave up to concave down. It could change from concave down to concave up. Let's see, do we have any other formations? I'm sure we do. Concave up to concave down. And so this would be, if I can draw this a little bit more intuitively, we've got this last piece here. And they might all look really similar, but they're all different. So this side is the increasing side. And then this side, that's the decreasing side. But we've got, of course, concave up to concave down to concave up, and so on. So you can fill this out. So these are the 4 options you have for any point of inflection. Except it's just decreasing pieces. So if this purple one at -4, -4, they're all purple, but at -4, -4, if that one is supposed to increase, then we know it's one of those first options. So it could be like this, or it could be like this. We're not quite sure yet. So we'll hold on to that. And lastly, the clue is the second derivative of f is less than 0 for 0 to infinity. So this means it's negative. This means the second derivative is negative for 0 to infinity. So if the second derivative is negative, that means it's concave down for that entire interval. So, and that goes back to our notes up here, right? If it's concave down for the entire interval, 0 to infinity, then it's got to go through this point and keep on going through that point of inflection. I'm sorry, I marked the wrong point earlier, as that was a point of inflection. These two are the points of inflection. Silly me. Right, so then we can carry on with this. So this is all concave down here, and maybe I can draw that a little bit more, so it has a little bit more flex in it. There we go, concave down. So we go through that point, we have started at 0, 1 because we know it's concave down for that whole time. So that means we're able to start piecing this together because we know that the 2 pink locations are points of inflection where concavity changes. So if that piece on the right here, this is concave down, then this next piece that we draw in between has to be concave up. And then, of course, we have to go back to concave down because, and I know it might be confusing with that open circle and closed circle there, but I'm just showing that those are points of inflection. So they're actually closed circles. So there we have it. We have alternating concavity with that. All right, now based on the sketch you just made, how many locations exist on the graph where f prime of x is equal to 0? Or in other words, there's an extrema or horizontal tangent line. That's what it means when f prime of x equals 0. And we can pick these out. We've got a horizontal tangent line around here. It looks like there could be one at that spot. So this one is definitely more of a where is f prime of x equals 0 possible? That's probably how I should have phrased it. So possible locations could be at x equals -4 or on the interval, we'll just say from 0 to 3. Right. So that's going to be it for the practice here. I went a little bit more in depth on the practice because there's just so much that could be asked about this. So we are going to definitely have more group time and time to process this. This is probably what we'll be doing for the remainder of the year, and it's not very long, but we'll try and grasp this a little bit more before our test. So thank you for watching, and I'll see you all later. Bye.